Welcome everyone to 8th lecture of the series on motives in algebraic geometry by Growth and School. So this lecture is hosted by Maths Club at ISER Pune. Today's speaker is Dr. Vivek Mohan Malik, and the topic is triangulated categories. This topic is quite independent of previous lectures. So even if you have missed any, you can still follow these lectures. Okay, so now I hand it over to speaker.
Okay. Thanks for inviting me and giving me this opportunity. I can see a whole range of people on this side. I don't know, I checked online. So for some people, this talk will be very trivial, and some people it might be a bit, but I'll try to make it as accessible as possible. One thing is, it's a bit abstract, so I'll start with some examples and then sort of write down the definition in the middle of the lecture and then go on to properties and yeah, so let's see how it goes. Right now triangulated categories is quite an old subject, so there are a whole lot of books and my lectures are taken mostly from these LMH lecture note series 375. So 75 by Tom Ferguson, and yeah, so it's a nice summary of the category, a triangulated theory of triangulated categories, and I'm summarizing that. So it will be a bit fast, but it's okay. So okay, so I'll assume that you know some abelian categories, but if you haven't heard those lectures, all you need to know is that if you have a ring and the modules over them, then these modules form an abelian category, and that's more or less the example you should keep in mind right now. And okay, so let's fix something. So let A be an abelian category. Okay. So example are modules. Okay. And so now I'll construct the first example where triangulated category comes from. So you start with category of complexes, right? So what is the category of complexes of an abelian category? So we will construct a category CA whose objects are basically everything of the form. So you have a bunch of objects A n plus 1, an minus 1, and so on, where AIs belong to the category A. So and these morphisms are from A as such that. So let me give these morphisms some names. So I'll keep the index as the index of the source. So dn is from an to n minus 1. So you will have dn composed with dn plus 1 equals to 0. So here, this the complexes extend on both sides. So it's indexed by z. So there, this will be. So it will be indexed by all integers. Okay, so right, and then so these objects are not completely abstract. So, so when you do some homology or cohomology theory, you will see that to construct those invariants of topological spaces, so you actually look at you create these complexes of abelian groups and you work with them. You define something. So we are trying to capture similar objects in this theory. So this is the most basic object to start with, and then the morphisms are basically you can guess, like, so there's no 0 here. So you have objects are of the form. And so on. And below, take another object, maybe bn plus 1, bn minus 1. So index wise, there will be maps, phi n plus 1, phi n minus 1, such that all these squares commute. That means, so you can go from an plus 1 to bn in two ways. So no matter which way you go, you either go from an plus 1 to an to bn. That composition of functions is same as an plus 1 to bn plus 1 to bn. Okay. So morphisms are basically collections of phi n such that this commutes. Okay. Okay. So yeah. So now we can one can check that this category is also abelian. So I won't do that. So I'll just write it as a fact that CA is an abelian category. So you can define kernels, co-kernels, and then it satisfies the condition that co-image is image. So it satisfies all the axioms. Okay, so now when you do algebraic topology, the first thing you prove, okay, is that if two topological spaces are homotopically equivalent, their cohomologies match. Okay, so and this is sort of an abstraction of that. And then if you see the proof of how you prove that homologies match, there's a particular construction, okay, which gives rise to the notion of two chains being homotopic. So I won't go into the topological intuition. So I'll just write down the definition of two maps being homotopic. So let me. So this definition is much more down to earth. Means we don't have to define homology theory for that. But yeah. So let x dot and y dot be two complexes. Okay, and so yeah, and suppose we have two maps. We want to say we want to define an equivalence relation. We want to say when these two are equivalent. So what we do is that you write. So I'll draw directly in the diagram. So maybe. So this is the first one. This is the second one. Okay, and okay, and then you have these two functions. Okay, I won't write the indices because it's sort of getting cluttered. So I'll just write f, and the indices are clear from the context. Okay. And then by homotopy, the way the chain homotopy works is that for each n, you construct something, some other color maybe. So you construct maps like this. Okay, so you have all these at SS, where such that, so what happens is, so Gn minus Fn becomes, so let me call this dyn plus 1, things like that. So, and this is dxn. So this becomes Sn minus 1 compose dnx. So you do this plus dn plus 1y compose Sn. Okay. So there's the pointer here. Okay. So so basically, to go from xn to yn, you can either come back to yn plus 1 and take the differential, or you go to xn minus 1 and then take s. So if you add these two compositions, you should get the difference of the two maps. So now okay. So it turns out that whenever this happens, so now you can define homology of a complex as you look, so you know that dn, okay, so maybe I'll just quickly talk about this. So so recall dnx composed with dn plus 1x is 0. So that will imply that image of dn plus 1 is inside kernel of dn. Okay, because if you take dn on the image, you get 0. So therefore, and so therefore we can look at this. So basically look at the co-kernel of this inclusion. So I'll just write it like this. This is defined to be the Hn of the complex. Okay. Okay. So what it says is that, and then there's okay. Okay. So let me now go back here. So now suppose you have a morphism of complexes. So this you must have, so people who attended, I think, Umesh's talk or Sarang's talk, you might have seen. So okay, so I'll just quickly say what they did. So whenever you have injective resolution of two objects, if you have a map between the objects, it induces a map between the resolutions, it induces a map between the corresponding homologies. Okay, so that's what they did. So I'll do the same construction just to relate it to what has been done before. But, I'll just quickly recall what it happened there. So let me write. Okay, so I'm writing up. Okay, so. So you have the other ones also. Okay. And suppose you have maps, chain map. Okay, so then one thing you see is that if you so then assume these are like modules, so you can prove it with arrows also. So if you have if this commutes, then you can show that Fn induces another map, okay, from kernel of dxn to kernel of dyn. Okay, so if these were modules, it would be easy to check, because if you take x in the kernel of dnx, it goes to 0 in xn minus 1. So now look at its image. So now so x goes to say y. So now the image of y here is same as you go to xn minus 1 and come back. So it will be 0 because it goes to 0 in xn minus 1. So this will go to something. So d of y is equals to fn minus 1 of dnx of x. But this is 0. So this, and this is a module homomorph. So this will be 0. So for modules, it's easy to check. With arrows, you can just do some diagram chasing, it will work out. So you can prove it using the universal property of kernels, but okay, so let's not go into it. Okay, and then similarly, and finally, this fn square bracket fn induces an fn bar, or I'll write it at fn star from kernel dnx mod image dn plus 1x to kernel dny mod image dn plus 1y. So this is defined to be h and x. This is defined to be h and y. So this is basically saying that if you have morphism between complexes, it induces a map between the homologies. Okay, and then the fact is that so if f is equivalent to g, then it induces the same map. So therefore, since we are trying to capture homologies theory in some way, you want to look at a category where these equivalent things are actually equal. Okay, so you want to create a category where homology is a very natural thing, like, okay, so to study. So so that leads to the notion of what is called homotopy category of an abelian category. Okay, so before going into the homotopy category, I need to give some facts. So actually, given the definition, given this definition, these facts are easy exercises. So maybe if you're interested, you can do this. So the factor, so A is that this is an equivalence relation. So F is homotopic to G implies that, so suppose these are from X to Y, and then alpha be from some Y to Z, then that implies that alpha composed with F is homotopic to alpha composed with G. And similarly, this is the same thing. F homotopic to Y from X to Y, and beta is from W to X, then beta composed F is homotopic. So why am I doing? I'm doing all this. So finally, I want to say that if and F prime are homotopic, and G and G prime are homotopic, and you can compose those maps, then G prime compose is homotopic to F prime compose F. Okay, so that then finally put all these together and say that F is homotopic to F prime, G is homotopic to G prime, implies G compose F is homotopic to G prime compose F prime, provided the maps are composable.
Professor, in C you mean F compose?
Yeah, so this we will need to make sense of what whatever I'm defining now is actually a category, because in category you have to compose maps, and if the composition is not well defined, then it's of no use. So so these will help us to see that this definition makes sense, that so E is an abelian category, and then K, okay, K again stands for complexes, but C was used up, so K is basically has this. So we want to construct this. So here the objects of K are exactly the same as objects of C. Okay, and but the morphisms. So if you want to look at the morphisms between two complexes, objects of C are just complexes. So if you have two complexes, and then the morphism in the category Ka is exactly same as you look at the morphisms as complexes, and then go modulo this equivalence relation. Okay. And so now, since we showed that if two things are equivalent, if you compose equivalent things, you get equivalent things. This is a well-defined category. Oh, okay. And okay, so this is good. We are closer to sort of understanding homology using this, I guess. But now the problem is that K is no longer abelian. Okay, right. Okay, so yeah, so I maybe if at the end, if there's time, I can give you an example. So I'll give you the example, and maybe the proof that it's an example we can discuss later. So you look at these two complexes of abelian groups. So now I'm taking A to be the category of abelian groups, or Z modules, and then you take this to be equal, and all the other maps are zero. So this is a morphism of complexes, and then one can try to prove this does not have any kernel. So if you try to prove that it is a kernel, it leads to a contradiction. Okay. Okay. So we are very close to defining triangular categories. So K loses its abelianness. It's not abelian anymore, but it has some other structure. So whatever the other structure, we will capture it as a triangulated structure. So so define the triangle. So I need something called a suspension. So so for complexes, the suspension is so if X is equal to the suspension of x, which is either you write as this or this. So you suspend once, you shift by one. This is exactly this. So note that I'm keeping the degrees same. So I'm shifting to the left, everything to the left. So in particular, x dot one, x dot one, the nth element of x dot one is just x of n minus one. So you shift the whole complex to the left. Means whatever was at zero, you put it at minus one. And so, okay. So why do we need the suspension functor? Right. But in general, we want to define everything categorically. So note that this shifting is actually an equivalence of category. It's an auto equivalence. It's a map from the category to itself, which has a quasi. It actually has the inverse. So okay. So definition. Category is it's an additive. Okay, so this we don't need abelian for this. Category C along with okay. So now that we are going into, so we want all these functors to respect. So we are in the abelian category setup, or at least the additive category setup. So so that basically means the homes have an abelian group structure, right? So if the homes have an abelian group structure, you want all the functors to respect that. Okay. So we want the functors as that when you go from home AB to home FA, FB, that induced map from the functors, that should be a group homomorphism. So we want to keep this adjective additive. It exactly means that it's a homomorphism functor sigma from C to C. Okay, which is an automorphism. Okay. Okay. So here actually what sort of you can take the intuition again from topology, like if you do homology theory, if you have a okay, so if you have a short exact sequence of chain complexes, so when you take homologies, you get a long exact sequence. So you get from HNX, HNY, HNZ, then you end up in HN plus 1Z. So which is you shift the whole complex to the up slightly. So you're trying to capture that in some sense, right? Okay. So okay, so now define a triangle is a collection I'll just say is a diagram of the, means it has 3 objects and 3 morphisms, so which you can put in diagram like this. Of the G, Z, and then sigma X, okay? And it's H. And of course, so once you have this, from sigma X, you have a map to sigma Y, which is sigma Fs. Sigma is a functor, right? It's an auto functor. It's a functor from to itself. So technically, you can continue this. So, and so on. So, and so on. So it becomes, and then also, since it's an equivalence, you can put sigma inverse Y here. But we don't write that. Okay, we'll just write this. I mean, giving this information is there. Okay. But we will capture what happens when you do that. Okay. So, and then usually it's you can also denote the triangle by this. So there's a notation. So you have if G H, the plus 1 means H does not map from Z to X, but it maps from Z to sigma X. Okay, and a morphism. So these are all triangles. These any such diagram is a triangle. Yeah. So after sometimes I will talk about distinguished triangles. There's a particular subclass of triangles. Okay. So a morphism of triangles is basically like a morphism of complexes. Triangles is this. So you have so it's basically a triple. So if I psi rho. So you have, suppose you have two triangles. I'm not writing the maps. Okay, so they're triangles in the same category. So the sigma is the same thing. Okay. And then you have phi, psi. All of this should come. Okay, all the square should come. So it's like complexes. Till now it's okay. It's a definition just this. Okay, and then okay. So now I can define triangular categories. So it's sort of like, so we don't know which of these triangles actually have any geometric information. So you, instead of so you just say, like in topology, you say that okay, these subsets are open sets, and then you work with that. Here we will say that these triangles, certain triangles are distinguished, and they should satisfy certain axioms, like open sets of axioms. And then you work with. So what are the axioms? There are usually four axioms, but in this LMS notes, there are 5 axioms. They broke it up into more things. I found that better, so I am giving 5, actually 6 axioms, because there's a 0 also. But but all the definitions of triangular categories are equivalent. So I'll call this a pre-triangulated category because a lot of properties hold for them. You don't need the last axiom for certain properties. But if you want to work, but the last axiom is also important. So I'll give that later. So a pre-triangulated category is, so what does it have? So first, an additive category. So note that we lose abelianness, but we want to return, even in Kx, what were the homomorphisms in K? Means you start with an abelian category, look at the homotopy category. What were the homomorphisms? They were basically homomorphisms in Ca, which was an abelian group, modulo and equivalence relation. You can check that it's still an abelian group, and it forms and composition respects the addition and so on. So it's still an additive category. So we keep that. An additive automorphism, sigma from T to T. This is the suspension. So it's a suspended category. So we will call it translator shift. Okay. And the collection of distinguished triangles. Okay, says that. So we have to sort of know how to figure out something is distinguished or not. So we give the basic ones, okay, which are distinguished. So A. So suppose you know some distinguished triangle. So then any triangle isomorphic to a distinguished triangle is distinguished. Okay, so okay, this we need. This is sort of, and then maybe I should keep track of the correct. As I said, if you look at some other book, this TR numbering might be different. So anything of this form is distinguished. And by 0, anything isomorphic to such thing is also distinguished. So in particular, if you have x and x prime which are isomorphic, then x, that isomorphism to x prime to 0 to sigma x, that's also distinguished. Okay, so it follows from that. So then, and then the other thing is that you start with any morphism. So if f from x to y is a morphism, P, then you can complete it into a triangle. There exists a triangle such that where you have this, then some z, okay, and then okay, and in case of homotopy category, I'll tell you how to construct this set. Okay, so okay, this is there. Then tier 3 is that. So as I said, that if you have x to y to z to sigma x, so I wrote it like a triangle. So you think that you can rotate the triangle. So this is exactly the rotation axiom, which says that if this is a distinguished triangle, okay, distinguished, if and only if. So you can rotate it, but you have to be a bit careful so that computations work out. So I'm writing sigma here. So you'll have sigma y, and you can guess this map will be sigma u, but this is not distinguished. You basically correct with the sign minus, which is a bit difficult to discuss. But when you actually work out for the properties, and then you will see that this works. You need this sign for things to cancel. So okay, right. And okay, and the other one is that so we saw that if you have a morphism x to y, you can complete it into a triangle. So now suppose you have two triangles. So given a commutative diagram, okay, maybe I should do it in the next page. Okay, given the commutative triangle, so you have x to y to z. I'm again not writing the maps, and you have x prime to y prime. Okay, and suppose you have morphisms like this. Okay. Right. So then, and this commutes, so then automatically get a morphism here. So there exists a map such that everything comes. So you basically, if you have a commutative square, you can complete into a commutative triangle. Okay. Okay, morphism of triangles. That's yeah. Okay, right. So these are the axioms. And one thing I want to say that I just said there exists. I didn't say it's unique, and that is important because in examples also there's no way of giving a unique map in most cases, and so there can be multiple maps which satisfy this property. Okay, so okay, so then one more axiom. These are the basic axioms, and there's one more axiom called the octahedral axiom. I'll come back to that in a few minutes. Okay, so let's try to study these for some time and prove some properties. Before that, let me tell you. So we should always have some example in mind. So, so I want to say K satisfies these axioms. And then you might ask, like, okay, so the thing is that what are the distinguished triangles in K? So K is just the additive category. So what are the distinguished triangles? So you do something called the construction called a mapping code. Okay, so you suppose you have yeah. So maybe I write it x dot. So maybe I'm using xy for that. So maybe here dot b dot be a morphism. So let me start with morphism in CA because there's I can define the mapping cone in CA. It gives a triangle in K. Okay. So then you can construct what is called an M of F dot. Okay. So this is an object. Okay. Which where M of F dot n is nothing but you have Bn direct sum n plus 1. You want to go to -1. Okay. So we are looking homologically, so n minus 1. And then so I have to make it into complex. I have to give you the differentials, right? So d n mf is from, so it has to be a map from Bn direct sum n minus 1 to Bn minus 1 direct sum n minus 2, right? So so I can write it as a matrix. So let me write down the matrix and then I'll tell you how it's implemented. So Bn to Bn minus 1 is just dB. And an minus 1 to n minus 2 is dn. And then you have a map from an minus 1 to bn minus 1. So that is fn minus 1. That you put here. You remember that. And bn to n minus 2, there's the map. So you put it 0. So it means this is the obvious thing you can write without knowing anything else. So this you can always write. And this is, so what does it mean to say a matrix like that? That just means that if you, any object in the direction is of the, from BA, so you just send it to dB plus FA, comma dB. So this is the map. This is I wrote as a matrix. So means B goes to dB, and then f of A also lies in B, and then so okay. So okay, fine. So and then what? So you say that in K, a triangle is distinguished if and only if it is isomorphic. To triangle of the form. So you have A dot, you have some complex map of A dot. You have a complex map to B dot. Then of course, note that, yeah, so I'll write these maps. So let me write alpha to M F dot, and then there's a beta F, sigma A dot, where what is alpha F? So note that M F dot N was nothing but B N direct sum n minus 1. Okay, so therefore you just project. I mean, this is just so you have a map from Bn to here, which is say In. So alpha F is just this map, and then from here you have a map A to n minus 1, which is same as A sigma A dot. So this is beta. This gives beta. Okay, so it's just inclusion and projection. So anything of this form, you call it a distinguished triangle. And okay, so right. Okay, so it's not very, means it's not difficult to prove that all the facts hold, but it's just tedious computation. It's long, so yeah. So I won't do that here. You can go back and read. It's an easy diagram chasing kind of computation. So but what kind of arguments go into that? So for that, properties of pre-triangular categories. So you see, in complexes, composition of two adjacent morphisms is always 0. Okay, so here you can ask. So suppose you have a triangle. at the composition of adjacent morphism 0 means, of course, it's not given in the axioms, but we know axioms say that something. So the result is this. So p comma u is 0. Actually, I'm writing it different because they are 0 in different home sets. Okay. And then, yeah. So, and then this with the rotation axiom, sigma u compose w is 0 and so on. So you can get a whole lot of secret. So how do you prove this? So this is kind of trick. So you can. I'll give a proof of this because it's easy and fast. So you rotate this triangle. Okay, so you get a triangle like this. Sorry. Okay, and if you remember, this is V, this is W, and this is minus sigma U. Okay, here the minus one play a role. Okay. And then, and we also know that there exists a triangle. So this is equality. Then you have the 0 map to 0 and sigma z. This is a triangle by one of the axioms. Okay, and now you can look at these maps. So here you put V, and here you put equality. This commutes. Okay. So then the other axiom will say that there exists a map. So this commutes, and so this commutes. This implies that there exists something which completes it. So okay, okay. So, but here actually there's only one choice. Means it has to be the 0 map. So this is 0. So this is a triangle. This is a morphism of triangle. So everything commutes. That is the upshot. And then you note that if you look at this part of the triangle, you get that sigma v composed with minus sigma u is 0. Okay. So that will imply that sigma of minus v composed u is 0. From that you can say v. I mean sigma is an auto equivalent, so this is 0. So similar. Okay, no, that is part of the axioms, and as I said that it's there to make certain things work. Certain things cancel out. So, yeah, right. Means you can start developing this theory without the minus sign, but then you have to put minus sign somewhere else. So then you try to reduce the number of minus signs you introduce. So this works better. Yeah. No. So minus sign is only over here. This is just the translation. Next, okay. The thing is that this not putting minus is fine because this will also get a minus sign. So, so if you means this is negative of whatever comes here. So things match. So you don't have to put a minus in this one. Okay. So the other property is that okay, so a lot of these things hold. So now suppose again T is a triangular category, and x2, y2, z to sigma x is a triangle, and suppose T is in P. Okay. So then we can write down this complex, right? So you look at, so let me write down this first. This is easier. T comma x to home T comma y to home T comma z. And then you can get a map to home T comma sigma x. And here also you have maps from home T comma sigma inverse z by rotating the triangle. Okay, and so on. Okay, so it turns out that, and the maps are basically just compositions. Okay, you have a map from x to y, So if you are given a map from T to X, you compose with the map from T to Y. So this is a composition. So we compose, I think, if the U, V, and W, this is compose U, compose V, compose W. Did I write? No, it should be U compose. Okay. And the result is that this with the previous thing, this, this is a complex because V compose U is 0. So any adjacent, this is a complex. So this complex is exact. This is slightly longer proof than before, but the ideas are similar. Yeah. And okay. Which ones I want to tell. Okay. I have little less than 15 minutes. So I'll say only one thing. Okay. I'll skip the monastic part and just tell one more thing. So let FGH be a morphism of triangles. So then you can, okay. So then what so if F and G are isomorphisms, that implies H is an isomorphism. So it's like five lemma, and the proof of it uses 5 lemma. So, okay, so that is there. Okay, so let me quickly go to the last axiom. At least that should be there. And okay. Oh, I prepared in one order and I lectured in another order. So okay, fine. So right. Okay, so now the octahedral axiom. Okay, so I'll write down the axiom and it's up to you to draw an octahedron out of all the maps. So, okay. So suppose you are given two distinguished triangles. Distinguished triangles. So X to U to Y to, okay, so I need names. Okay, I won't write down all the names because then it becomes cumbersome. So I'll choose the ones which I'll use in the diagram. So now Y. So see, these are composable maps, X to Y, Y to. So this I'll put a prime. Okay. So now look at YZ. So this is like, you take X to Y, you choose any triangle with that. Then take Y to Z. Now look at a triangle like this. And note that the name I'm giving this is the one which is left out. So Y to Z, X was left out, so I called it X prime. And now look at the composition map. So that will map to Z, and this will be Y prime, and this will be Z prime. So you make look at these three distinguished triangles. Okay. So now the octahedral axiom will say that we can make a triangle out of these new objects which you create. It means, okay, the cones form a triangle. So then there exists a distinguished triangle. Z prime to Y prime to X prime to sigma Z prime, says that this is not enough. You need some compatibility, some commutative diagrams. So the commutative diagram is this. So it's a huge one. So what you do is that you put these given ones in the first 3 rows. So no, not the, so I want this triangle to be there, right? So so what I do, so I put the other one, x to z to y prime. Then now we put the third one, which is y to z to x prime to sigma y. Okay, and then finally z prime to y prime to x prime to sigma. This is the new triangle. And now vertical maps are in sort of wherever there's equality, you put equality. Well, okay, here there's an equality. And then the other maps are sort of given. So y to z is v, okay, and x to y is u, and everything will, so no, this is u, this is v, hey, sorry, this is v compose u. And this is u, so this is v. Y2z prime is given by this map. So these maps are same as ones here. And these maps get filled in because of the triangles. So this whole thing commutes. Okay, because you have commutative squares here, you can fill up this, and the whole thing commutes, and this, as that last line is an exact triangle. This is the sigma of this. Okay. So this is one of the formulations of the octahedral axioms. So there are some equivalent formulations by Niemann and so on. So yeah, but they're all equivalent, but some of them are easy to check they're equivalent, some are not. But yeah, there are some equivalent things, but I won't go into that. So right. Okay, so I'll quickly say one more thing. Last time I said that when you have two homotopic maps, means few minutes back, it induces the same map on homology. So that property says that you have functors Hn from Ka to A, okay, which is basically you look at kernel of Dn mod image of Dn plus 1. So A dot goes to the co-kernel of this induced map. Okay, so now yeah, so so the Hn in Ca induces Hn here, and this is well defined. Okay, and so a morphism if is said to be if Hnf from Hnx to Hny is an isomorphism for all n in Z. Okay. So people who have done this did the injective resolution, projective resolution lectures, the aim of those lectures was, suppose you have a complex, you create another complex where each object is either injective or projective, but it's in the same quasi-isomorphism class, means the homology is matched. Okay, and then we proved that you can define derived functors using that. So that's the motivation. So we want to understand quasi-isomorphisms. And the thing is, so the way quasi-isomorphisms are defined, if you want to understand homology, so you want a category, so the the nicest category which will capture homology is one in which quasi-isomorphisms are actually isomorphic. Okay, so it's difficult to naturally find some such thing. So you artificially invert them. Okay, so this process creates a new triangulated category called the derived category. So, so one can invert quasi-isomorphisms, create category DA. Okay, so which is also triangulated. But that is a okay. Okay, fine. So okay. So there are two things I can do from here. I have only 3 minutes. So okay. Right. So maybe I'll so I cannot prove anything in 3 minutes. So I can tell you, so what the way you invert quasi-isomorphisms is that you check certain properties for quasi-isomorphisms, like composition of quasi-isomorphisms, quasi-isomorphism. And then if you have a diagram like this, like x dot to y dot to, and any map, and this is a quasi-isomorphism, then you can get some other object here so that this becomes a quasi-isomorphism and this comes. So you can make squares like this and so on. So there are a bunch of axioms. And so which are like, if you have done some commutative algebra, it's sort of reminds you of multiplicatively closed sets. So you can then define morphisms. So then you basically define a new category where the morphisms are of the form this. So a morphism from x dot to y dot is something of the form there exists some w dot. So there's a quasi-isomorphism here, and there's a usual map here. And then you have to define composition. So then you have some z dot here, some g r. Then you have some u dot. So then because of you can construct squares like this, you have something here, v dot. So this is a quasi-isomorphism. And then this composition becomes a quasi-isomorphism, and this is a morphism. So this is again a map of the usual form. So yeah, so this is the construction. But as you can see that now we have arbitrary objects coming into play, and categories are objects of categories usually are not sets, so you run into set theory problems. But there are ways to get around it. That's the whole theory of localization. So maybe I'll end here. Okay, I already finished. Okay, but yeah, so the idea is that okay, so one can make this work out at a certain, okay, especially if categories are small, essentially small, everything is okay. Like objects, you can, if you can put everything in some kind of Grothendieck universe. Okay, right. And then the fact is that whatever category you construct by inverting all these quasi-isomorphisms, so this dA obtained from quasi-isomorphisms is also triangle, is a triangle. Okay. And there's a whole lot of ways you can get triangulated categories otherwise. So there's something called Frobenius categories. Those are like additive categories. Yeah, you can take abelian also, where projective objects match with injective objects. Projective and injective are the same. And then from Frobenius category, there's some Hiller's construction, and you can create. So there's triangular categories come in a lot of different ways. So in algebraic geometry, it mostly comes as derived categories. Then in representation theory, it comes via these Frobenius categories. Then you have the stable homotopy category coming from topology, which is triangulated. So triangular categories are everywhere. And even if you are interested in analysis, C-star algebras have this bivariant KK theory. And the category, certain categories of C-star algebras where the morphisms have these KK groups form a triangulated category. So these are Okay, so this is something.
Online participants might have.
Okay, okay.
Can you please volume of your
Okay. So,
Is there any question from the online participants? Okay,
okay.
maybe not. So with this KK theory coming up, actually we're going to make an announcement about K theory, maybe today or tomorrow.
Okay.
So that's an upshot. Apart from that, thanks for this wonderful lecture, Professor.
Thank you.
Okay, then. So we end our session today here.
Yeah. Okay. So, bye.